Welcome to this video about properties of the elements. In this video, we'll go over both chemical and physical properties of different elements and try to relate them to their positions on the periodic table. We'll go over what differentiates a metal, a nonmetal, and a metalloid, covalent and ionic bonding, what defines a transition metal, the elements in groups 1 and 17 to give us an idea of how properties change down a group, the elements across period 3 to give us an idea of how properties change across a period, and we will end with a discussion on the acidic and basic oxides of the elements across periods 2 and 3. So let's jump straight into it. The periodic table can be divided into metals, semimetals, otherwise known as metalloids, and nonmetals. We will first talk about the metals. In metals, atoms donate their outer electrons to a delocalized sea of electrons. In metallic bonding, the positive metal nuclei are mutually attracted to the bonding electrons. Metallic bonding thus requires the removal of electrons from the outer shells, so it can only occur if the electronegativity and the ionization energy are small. Both parameters increase across a period and decrease down a group. Therefore, metals are found to the left and bottom of the periodic table. On the other hand, nonmetal atoms gain full outer shells by sharing electrons in directional covalent bonds. Nonmetal atoms contain many electrons in their outer shells, so they can gain full outer shells by forming a small number of bonds. An element is a nonmetal if its electronegativity and ionization energy are high. Nonmetals are only found at the top and right of the periodic table. And what about the semimetals? Semimetals, or metalloids, are elements with properties between metals and nonmetals. They are often shiny like metals, but resemble nonmetals in their chemical reactions. They are also semiconductors, becoming electrically conductive when the energy input or voltage is sufficiently high. The metalloids are found in a zigzag from boron in period 2 to polonium and astatine in period 5. Some groups contain a mixture of nonmetals, metals, and metalloids. For example, group 14 contains a nonmetal, carbon, 2 metalloids, silicon and germanium, and 2 metals, tin and lead. The metallic behavior increases down this group. Now let's revise a couple more types of bonding. Bonding depends on the properties of the elements involved in that bond. The type of bonding between atoms depends on the electronegativity difference given the abbreviation delta X. Ionic bonds occur if the electronegativity difference is large. If the electronegativity difference delta X is greater than 1.8, this is indicative of an ionic bond. On the other hand, covalent bonding occurs when this difference is small. A delta X of less than 1.8 is indicative of covalent bonding. If this delta X is between 0.5 and 1.8, the bonding electron density is much higher around one atom than the other, making the bond covalent but polar. For some metals, the electronegativity is high enough for the atoms to form polar covalent bonds. This is true for the D-block metals and the period 2 metals lithium and beryllium. For example, beryllium chloride is covalent even though magnesium chloride is ionic. Now let's move on to discussing the transition metals. The transition metals are an important class of elements found in the D block of the periodic table. These metals have partially filled D subshells or form stable ions with partially filled D subshells. For example, copper forms copper 2+ ions with 9 electrons in the 3D subshell. By contrast, zinc and scandium are not transition metals, because the stable zinc 2 plus ion contains a full 3D subshell, and scandium 3 plus does not contain any d electrons at all. Metals in the d block form polar covalent coordinate bonds with nonmetals to produce complexes. For transition metals, these complexes are colored. In this next section, we will talk about a couple of the groups found on the periodic table. We'll start with group 1. It contains the alkali metals. The alkali metals are soft metals with low melting points. The metals are in the same group, so have similar chemical properties. All metals in group 1 lose 1 electron in reactions to form 1 plus ions. For example, sodium reacts with water to produce a sodium ion and hydroxide ions and hydrogen gas according to this equation here. The atomic radius increases down the group as the number of shells increases. So, for example, lithium is smaller than sodium, and sodium is smaller than potassium. As the atomic radius increases, the ionization energy decreases as the outermost electron becomes easier to remove as it's further away from the nucleus. The decrease in ionization energy means less energy is needed to form the 1 plus ion in reactions, so more energy is released overall. This means that the metals become more reactive down the group. Whereas potassium reacts violently with water, producing a lilac flame, the reaction with sodium may not be exothermic enough for the hydrogen to ignite. And what about physical properties? Alkali metals are soft and have low melting points because the atoms are large and each atom only contributes 1 electron for metallic bonding, meaning that the attraction between the atoms and the bonding electrons are weak. The number of outer electrons stays the same down the group, but the atom size increases and electronegativity decreases. Therefore, the delocalized electrons in the metallic bond are attracted less strongly and the melting point decreases. On the other side of the periodic table, we have group 17, which contains the halogens. The halogens are nonmetals with low melting and boiling points. All halogens are normally found as diatomic molecules. Halogen atoms have 7 electrons in their outer shell, so forming a covalent bond gives them a stable octet of electrons. As in group 1, the atomic radius increases down the group and the electronegativity decreases. Bonding electrons in a halogen-halogen bond are further from the nucleus when the halogen atom is large, and this results in a weaker and longer bond. The fluorine-fluorine bond, however, is an exception here. The atoms are so small that there is a strong repulsion between the lone pairs of the 2 atoms, causing this bond to be weaker than the chlorine-chlorine bond. The electron affinity becomes smaller, i.e. less negative, down the group, as less energy is released when an electron is added to the outer shell of the larger atoms. Therefore, the elements near the top of the group form anions more readily. This trend in electron affinity results in a reactivity series for reduction reactions. The reactivity decreases down the group. Electrons are transferred to convert the most reactive halogen to its anion. For example, reacting fluorine with chloride ions produces chlorine and fluoride ions according to this reaction equation here. The more reactive halogens also react more readily with metals to form salts. And what about the physical properties? Fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. The boiling point increases down the group even though the atoms are becoming larger. Unlike the alkali metals, the halogens form simple covalent molecules that are held together by dispersion forces. These forces are stronger for larger atoms. As larger atoms have more electrons, it's easier for these electrons to be redistributed within the atoms to produce induced partial charges. In this section, we will focus on period 3, as by looking at period 3, we can see how the properties of elements changes as we go across a period. Across a period, the nuclear charge increases while the number of shells stays the same. The outer shell electrons are therefore more strongly attracted to the nucleus, causing the atomic radius to decrease. This increased attraction between the valence electrons and the nucleus causes the ionization energy to increase, and the electron affinity also becomes larger. The elements to the left of period 3, sodium to aluminum, are metals, while those to the right, phosphorus to argon, are nonmetals. Silicon is a semimetal, otherwise known as a metalloid. The melting and boiling points of the elements are shown. The metal atoms interact via metallic bonds. The lattice of positively charged nuclei are attracted to a sea of delocalized electrons. Melting point and hardness increase from sodium to aluminum because each atom contributes more valence electrons for metallic bonding, and the atoms also become smaller, so the nuclei are closer to the bonding electrons. Silicon atoms form a giant lattice of directional covalent bonds. This causes silicon to be more brittle than the metals, as it's more difficult for layers of atoms to slide over each other without breaking bonds. The bonds are stronger than metallic bonds, however, so the melting point is much higher. The nonmetals in period 3 all have lower melting points, because with the exception of argon, the atoms do not form a giant covalent lattice, but instead form discrete molecules. The atoms are linked by strong covalent bonds, but the molecules interact only by weak dispersion forces. Therefore, very little energy is needed to overcome these interactions and separate the molecules. Phosphorus forms a number of allotropes, in which atoms are linked in different ways. The standard state is white phosphorus, in which each molecule contains 4 atoms. By contrast, sulfur atoms form rings of 8 compounds. Because these sulfur molecules are larger, they form stronger dispersion forces and display a higher melting point. Chlorine is a smaller molecule still. The molecule only contains 2 atoms, linked by a single covalent bond. The dispersion forces between the molecules are therefore very weak, such that the molecule is a gas at room temperature. Argon atoms do not readily form covalent bonds, because the atoms already have a full outer shell of electrons. The element therefore consists of a single atom, giving it an even lower melting point than chlorine. In this last section, we will discuss different oxides. All elements in periods 2 and 3, with the exception of neon and argon, as these are noble gases, can react with oxygen. Sodium forms the oxide salt sodium oxide. Sodium peroxide and sodium superoxide, which are other oxides, are also possible but much less stable. Magnesium reacts with oxygen to form the salt magnesium oxide. These oxide salts react with water to form hydroxide ions in solution, making them basic. Aluminum oxide is a giant covalent lattice with highly polar bonds. Because it's not an ionic solid, it's insoluble in water. Aluminum oxide is amphoteric. This means that it acts as both an acid and a base, reacting with both acids, such as hot dilute aqueous hydrochloric acid, and bases, such as hot concentrated aqueous sodium hydroxide. The oxides become less basic across a period, because the elements become more electronegative, and their bonds with oxygen become less ionic and more covalent. As electron density is drawn away from the oxygen ion or atom, it's less able to donate electron density to a hydrogen ion in an acid-base reaction. The pH of a solution is a measure of the hydrogen ion concentration. A small concentration gives a high pH. Basic oxides produce solutions with a high pH because they react with water to produce hydroxide ions. These hydroxide ions react with hydrogen ions to increase the pH. Non-metal oxides include NO2, P4O10, SO2, and SO3. Nitrogen dioxide, NO2, dissolves in water to form a mixture of nitrous acid and nitric acid. The phosphorus oxide, P4O10, is a simple covalent compound with a cage-like structure, similar to diamond but one that doesn't repeat in all directions. It readily reacts with water to produce phosphoric acid, a moderately strong acid. Sulfur reacts with oxygen to form sulfur dioxide and sulfur trioxide. Both are acidic gases. They react with water to produce the weak acid sulfurous acid and the strong acid sulfuric acid. The oxides become more acidic across a period and down a group, especially if you only consider the reactions of the most oxidized compounds. For example, the acid strengths of the oxides we mentioned increases in this order. And that's it for this video on properties of the elements. We'll quickly recap what we went over. We learned where the metals, nonmetals, and metalloids are on the periodic table and their different properties. We also learned that ionic bonding happens when the electronegativity difference is high and covalent bonding occurs when this difference is low. We also learned that transition metals are metals with an incomplete d subshell. We then discussed how properties change going down a group. Group 1 was representative of metallic groups, and Group 17 was representative of nonmetallic groups. Next, we talked about how properties change when going across a period, using period 3 as an example. We also learned that across a period, the oxide character changes from basic to acidic. So, hopefully you learned something new about the properties of the elements in this video.